back again. This is going to be part number 6 and episode number 25 of Learning by Doing MPI. This was about chapter 7, which was basically about groups, context, communicators, and caching in MPI. So we're going to continue from where we left off. We talked about this MPI com split type and the MPI com type hardware unguided last time, and in this episode we're going to continue our discussion with MPI com create from group. So here the arguments that we take is basically a group handle. We get a string tag, and we get an info handle, we get an error handler, and we get a new communicator. Okay, every sort of parameter is an input unless the last one, which is a new communicator, is going to be an output. And you see that it says error handler to be attached to new intra-communicator. So this MPI com create from group is going to create us an intra-communicator. And the string tag again is a const char star, a CS style string. And then the error handler is of type MPI error handler. We haven't talked about error handling or error handlers in MPI. So I think that's going to be in more information is going to be in chapter 9 if I'm not mistaken. But let's see. MPI com create from group is similar to MPI com create group, and the difference between the two is that in MPI com create group we use a pre-existing communicator, and then we try to basically use a subgroup of that communicator to create our communicator. But in this MPI com create from group, we directly use this group to create our communicator. We don't need a sort of a handle to the pre-existing communicator. So it says that also of the new intra communicator is specified by a group argument rather than the group associated with the pre-existing communicator. So that was the difference. If a non-empty group is specified, then all MPI processes in that group must call the function, and each of these MPI processes must provide the same arguments, including a group that contains the same members with the same ordering and identical string tag value. Okay. So we do have an example for this one. It's called MPI com create from group. We have MPI com create from group. But before seeing the example, let's finish. If you have any extra, no, we don't have any extra discussion here. At least I haven't marked anything here. And the last thing we need to basically consider is the communicator destructors MPI com free, which we have seen already in trillions of our examples. So we don't want to spend time on this one because we have seen this thing already over and over. And then the last topic of this sort of communicators is going to be the communicator info, and then we're going to jump into inter-communicators after this. Okay, so let's go back and see the example of MPI com create from group. So these, we have already talked about them in all of our examples. So this is the world group. Again, we give the pre-existing intra-communicator MPI com world. We take the world group out of it. G size and G rank is the size and rank, and they are actually equal with rank and size if you ask the communicator as well. So this is the custom group that we want to create. Again, we want processes 2 and 3 to be in the same group. And we use the group constructor MPI group include with the pre-existing world group, and then we pass in 2 groups with these ranks, 2 and 3, into this custom group. And this is again to translate their ranks and see their equivalent ranks in the world group. So far, nothing new, basically. And then here we start to making a new communicator based on custom group. And here we use this MPI com create from group. So we pass in all the necessary arguments. For that call, you need to pass a group, you need to pass a string tag, you need to pass an info handle. Here we are passing MPI info null, and we are passing MPI errors are fatal. So this is a predefined error handler because we haven't talked about these error handlers. And as the name suggests, it basically is the case that if an error happens, it's going to be a fatal error. So then we have, let's say, finally the last parameter we need to pass in is the pointer of the communicator that we want to basically populate. And then we say if the custom communicator is not MPI com null, then you can ask for the rank, and then you pass the, for example, you just print something with the rank of that process. Yeah, and this rank is basically the rank in the MPI com world. And then this custom rank is the rank that it has inside custom group. So let's take a look at this example. Come create from group and MPI run. With 9 processes, you see that word ranks 2 and 3. These are the processes that we were interested to put inside our group and inside our custom communicator. And their corresponding ranks are going to be 0 and 1, which 0, again, 0 corresponds to process 2, and that's what it prints. And process 3 is also corresponding to process 1 in that custom communicator or in that custom group. Coming back here again, as I said, destructors, we don't want to talk about them because we have seen like in the freeing section always we see like MPI group free, MPI com free, you see MPI com free here, MPI group free. So same way for groups that they have destructors, communicators also have destructors, and that's it. So the last sort of subsection is communicator info. So you can basically assign some hints to communicators. So hints are specified via info handles. They're probably more discussed in chapter 10. Allow a user to provide information to direct optimization. Providing hints may enable an implementation to deliver increased performance or minimize use of system resources. That is super, super important. So the hints that you provide basically can help your MPI implementation. Either it's going to be OpenMPI, MPeach, or whatever, to basically do some optimizations. And what are those hints? Let's see first this advice to users. It says some optimizations may only be possible when all processes in the group of the communicator provide a given key info key with the same value. So it's just an advice. And then, I don't know, for some reason I put a question mark here because these two statements are exactly similar. So this advice to users, probably it's a, I don't know, a typo or a mistake in the standard. But these two exactly show the same sentence. Only the second one has all MPI processes. Here it says all processes. That's the difference. But what is important for us is that these keys that I don't want to go through all of them, but we're going to see like a couple of them, 1, 2, or maybe 3 of them. These keys are available or are valid for all communicators. For example, you can pass in MPI assert no any tag. As the name suggests, the no any tag, it means that you're in that specific communicator, you're not going to use basically the wildcard for tags. Let's see what it says. It says that this is a sort of a Boolean type of key. Default value is going to be false always. You can set it at true. If set to true, then implementation may assume that the MPI process will not use any MPI any tag wildcard on that given communicator. For example, the next one is MPI assert no any source. Again, similar to the other one, as the name suggests, no any source sounds like the wildcard any source, right? So default is false, and if you set it to true, then the implementation may assume that the MPI process will not use any wildcard for MPI any source in the communication in that particular communicator that you put that basically hints or info in there. So there is another list. For example, exact length is, you remember when we were talking about receiving messages, we said that receive buffer needs to have at least the size of the message that is being sent, or it can have more buffer size. So there's no restriction for that. But exact length basically says that, hey, all the messages that I sent are going to be exactly fit to all the receiving buffers that I basically acquire. So this can provide, let's say, more optimization. So you can take a look at the rest of them. There's like a couple of more, but they are like quite self-explanatory, and then once you read them, you understand what is the idea behind them. We're not going to spend too much time on that. Also, I don't have any examples for these ones because they're also quite a straightforward. It says MPI comes set info. So this is when you want to set extra information with the info handles to your communicator. I didn't see any complications here to provide any examples. So you have your communicator is an in-out in here because of obvious reasons, basically, because you pass in an info and then behind the scenes in that opaque object or that opaque data structure deep down in MPI, there's going to be some changes made based on the information that you pass in. And since the communicator is being used as an input and also at the same time as an output, because some changes are going to be affected to the communicator, then that is why it is marked as in-out. Okay. Also note that MPI, this is some important sentence here, MPI comes set info is also a collective routine. There's an advice to users. Setting info hints on the predefined communicator MPI com world and MPI com self may have unintended effects, as changes to these global objects may affect all components of the application, including libraries and tools. Users must ensure that all components of the application that use a given communicator, including libraries and tools, can comply with any info hints associated with that communicator. Okay. The cousin of set info is, of course, MPI get info to retrieve information or infos. Then communicator is going to be your input, and then the output is going to be info used. That's the new info object or the info handle that you get. So MPI get info returns an info handle containing the hints. It doesn't say the hint. It says the hints of the communicator associated with the current setting of all hints related to this communicator is returned to info used. So all the hints that basically you set for that communicator is going to be returned back into that info handle, right? So that is why we here it also used hints, not hint. An MPI implementation is required to return all hints that are supported by the implementation and have default values specified. Any user-supplied hints that were not ignored by the implementation also need to be added there as well. And any additional hints that were set by the implementation. If no such hints exist, a handle to a newly created info object is returned that contains no key value pair. Okay. So, and then the user is responsible for freeing the info used via MPI info3 operation. So these are some examples which we don't care about them. So we're going to pass. I think the next subject on the line should be the inter-communicators. So these are all examples. We don't care about them. Okay, yeah. 7.6, this section introduces the concept of intercommunication and describes the portions of MPI that's supported. It describes support of for writing programs that contain user-level servers. So we already talked about these stuff. We know that we have worked so far with intra-communicators, and in this section we want to basically work with intercommunication. So let's jump into somewhere. I think this paragraph basically, it basically shows what a local group is and what a remote group is, which we already in previous episodes, I think a couple of episodes before, we already talked about that. So you know that when in the context of intercommunication, you know what a local group means and what a remote group means, and we don't want to spend more time on that. All intercommunicator constructors are blocking except for MPI com idupe and require that the local and remote groups be disjoined. Okay. So this is a summary of properties of intercommunication. Intercommunicators, the syntax of point-to-point and collective communication operation is the same for both inter and communications and communicators. The same communicator can be used both for send and for receive operations, the first one. Second one is a target MPI process addressed by its rank in the remote group, both for sends and receives. So the ranks are going to be relative, right? So it's going to be based on the subgroup or group left, group right. Or let's say the ranks they have in local group and the remote group. The third one is communications using an intercommunicator are guaranteed not to conflict with any communications that use a different communicator. This we already have seen it and we talked about it. This is sort of the safety topic or concept that we talked about in MPI. The fourth one is a communicator will provide either intra or intercommunication, never both. This is also quite obvious. The routine MPI com test inter, so MPI com test inter may be used to determine if a communicator is an intercommunicator or an intra-communicator. Nice. Then this is an advice for implementers. But it basically let's shortly discuss this as well. It says for the purpose of point-to-point communication, communicators can be represented in each process by a tuple consisting of group, send context, receive context, and source. For intercommunicators, group describes the remote group. And source is rank of the MPI processes in the local group. So that makes sense, right? For intercommunicators, the group need to describe the remote group because we already know that what group A is, what the local group is. But the group what's it called, the tuple, that these tuple of information that we need, that group needs to represent, for the local group needs to represent information about the remote group. And the source is basically the rank of MPI processes in the local group. For intra-communicators, group is the communicator group because we don't have any remote and local, because remote is exactly as local. Source is the rank of MPI processes in this group, and send context and receive context are identical. Now, here, if we consider an intercommunicator cannot be discussed sensibly without considering MPI processes in both local and remote groups. Imagine we have an MPI process P in group P, which is intercommunicator CP, an MPI process Q with a group of Q and an intercommunicator of CQ. CP group describes group Q. So this is, you see, remote and then local group. So CP group describes Q group, and CQ group describes P group, and then CP send context should be CQ's receive context, and CP's receive context should be CQ's send context. And CP source is the rank of P in P, and CQ source is also the rank of Q in Q, okay? And how does it work? Assume that P sends a message to Q using the intercommunicator, then P uses the group table to find the absolute address of Q, source and send context are appended to that message, and then assume that Q posts receive with an explicit source argument using the intercommunicator, then Q matches receive context to the message context and source argument to the message source. So this is how it works. In the context of intercommunicators. Now we start with intercommunicator accessors. So the first one is MPI com test inter. We already talked about this. We said that this one is basically helping you to distinguish whether your communicator is an intercommunicator or is an intra-communicator. You're going to pass in your communicator in, and there's going to be a flag. The flag, it's set to be logical, but you see that it's an int star, so it's of type integer. But basically, if it's true, it means that it's an intercommunicator. If it's false, it's going to be an intra-communicator. Similar to, you remember that in intra-communicator context, we had this MPI com size, which basically retrieves the size of that communicator, or for example, MPI com group, the group associated with that communicator, or MPI communicator rank, which basically gives back or retrieves the rank of that particular process in that communicator. So if you use all these sort of operations with intercommunicators, and actually you can use them with intercommunicators, but the values returned by each of these is going to be basically the values in the local group. So if I have group A and group B, if I say MPI com size, if I'm a processing group A, it's going to give me the size of group A. If I'm a processing group A, it's going to give me the respective or associated group A, this call of MPI com group. If I'm a processing group A, it's going to give me the rank of that process with respect to or relative to group A. Okay, that's, I think, pretty obvious. This is, did we talk about everything here? It says table 7.1 describes the behavior an intercommunicator is used in an input argument to communicate described above on an intercommunicator. Furthermore, the operation MPI com compare. Okay, MPI com compare is also valid for intercommunicators. Both communicators must be either intracommunicator or intercommunicator, or else MPI unequal results. Both corresponding local and remote groups must compare correctly to get the results in MPI congruent or MPI similar. In particular, it is possible for MPI similar to result because either the local or remote group are similar but not identical. So this is not important. The rest of this stuff, it says that the following are local operations. These are provided consistent access to the remote group of an intercommunicator. So we said that MPI com size is going to give the size of the local group or group A. What about if we are a process of group A and we want to have information about processes in group B? Then you can use MPI com instead of size. You say remote size. it's pretty obvious, right? The name is self-explanatory. You already know that what it does. It basically, if you are a process in group A, you pass in the intercommunicator, and this size is going to be the size in group B, right? And if you are a process in group B, then if you use this MPI com remote size, it's going to give you basically the size of processes or the number of processes in group A. So this is pretty obvious. Then we have MPI com remote group, which basically gives the, let's say, the corresponding. Say if you are processing group A, if you use this sort of operation, it's going to give you the group associated with processes in group B. So this is also quite easy to understand. Although that here we have size, group, and rank, we have an equivalent for size. We have an equivalent for group, but we don't have an MPI com rank or remote rank. So the rank is not there, but yeah. So, so that is the symmetric access to both local and remote groups of an intercommunicator is important. So this function as well as MPI com remote size have been, yeah. So compared to those MPI com size, MPI com group, we have MPI com, yeah, we have MPI com remote size and MPI com remote group. Intercommunicator operations. This section introduces 5 blocking intercommunicator operations. MPI intercom create is used to bind 2 intra-communicators into an intercommunicator. We have used this MPI intercom create in pretty much all the examples that we had for scenarios of intercommunication, in collective communication and stuff like that. So we have like hundreds, I'm not even joking, hundreds of examples in that sense. So the next one is the function MPI intercom create from groups. The next one constructs an intercommunicator from 2 previously defined disjoint groups. Makes sense. The function MPI intercom merge, as the name suggests, probably it's going to take intercommunicators and then basically join them to create an intracommunicator. It says creates an intracommunicator by merging the local and remote group. So it takes a it takes an intercommunicator and it tries to merge the group A and group B into an intracommunicator. Easy to understand. The functions MPI com dupe and MPI com free introduced previously duplicate and free and intercommunicator respectively. So you can use also those operations on intercommunicators with the respective sort of semantics or semantics or behavior they have. Like dupe is for duplication and free is to free those resources. I put an X here because we don't want to delve into because most of this information are about those chapters that we haven't touched upon. For example, you see this is in section 11.2. This is the session model and stuff like that, or stuff in chapter 8, which is about those visual topologies and stuff like that. So we don't want to deal with those stuff. The first one on the line is MPI intercom create. I think I do have an example here. MPI com, intercom create from groups. I don't have an example for this one. Oh, now I do remember why I don't have an example for this. The reason for that is because we have used this so many times. We've used this like 100 times already. So let's take a look at this one, for example. Com create inter. This is one of those previous examples that we've seen. So when we try to basically make the original intercommunicator that we have, always at the end after splitting and creating that intercommunicator, we use this MPI intercom create. So that is why I don't have any example for this one, because we have used this literally in more than hundreds of examples, code examples. Okay. So you got to pass in your local communicator. You got to pass in your local leader. This is the same thing that we did here. And then you got to pass in the peer communicator. What is a peer communicator? Peer communicator is, so 24 minutes, 25 minutes is done on this episode. So probably I'm going to finish this example and description of this MPI intercom create, and then we're going to continue in the next episode. So you got to pass in your local communicator, local leader, and then the peer communicator. And then I was saying that peer communicator is basically the communicator that holds or contains both the local communicator and the remote communicator, or the local group and the remote group. In this case, once we are basically splitting our processes, MPI com world is basically containing group A, and also it contains group B. And then you gotta pass in remote leader. And one thing which is super, super important is that this local leader is the rank of local group leader in local communicator. So this is the local rank that they have. For example, in group A, the local rank of root is going to be 0, and in group B, the local rank of the group leader is going to be 0. Or it can be, like you can put also process 5 or process 2 to be the leader. But both of them in group A and B can be 0 basically. But remote leader, it's very, very important. This is the rank of that process inside peer communicator. So if I'm in group A, I say my local reader is going to be process 0, but my remote leader is going to be, for example, I don't know, if I'm using 8 processes, then it's going to be process, for example, 4. If processes 0, 1, 2, and 3 are in group A, and processes 4, 5, 6, and 7 are in group B, then every process in group A needs to pass remote leader as 4. If basically the 0th process in group B is going to be the leader. I think you get the idea. And then you pass in a sort of tag here, and then we have the new inter-communicator that we want. So easy to understand. So that is why I didn't have a separate example for this one, but it's quite easy. MPI processes should provide identical local communicator and local leader arguments within each group. Wildcards are not permitted for a remote leader, local leader, and the tag. Very, very important. And then I'm not going to continue with this one. We're going to go to the next episode because 25 minutes mark is already done. Okay.